So we're working on approximating and computing the area underneath the curve. Now this is R1. Like if we were just going from interval 1 to 3, here is a rectangle that we can find the area of. Now it's not going to be very accurate because there's a really big part of the area outside of our curve. So anyways, see that the area is 18 right now? If we had two rectangles, then our area dramatically changes. And now we have not as much of the rectangles outside. If we had 3, again, it changes slightly. It doesn't change as much this time. And now we have even less area outside of the curve. If we had 4, then 5, then 6, you can see that slowly but surely we're getting less and less area outside of the curve. And our area under the curve is actually getting more and more exact. Check it out. That's right side. If we did left side, it would look like this. That would be our first box, our first rectangle. And then see the area is only 2. And then we keep increasing it. As we increase it to 6. This first of all, this right here shouldn't say R6. It should say L6 because these are left side ones. But we're getting closer and closer to the same number that the other one got to. Do you guys remember what the other one ended on? 10.7. So we know that the area underneath this curve between 1 and 3, actually I want something that's a little more, we know that this area right here is between 7.37 and what was the other one? 10 point what? 10.7. So it's between these two. We know the area is less than that, but it's greater than that. All right, so whenever you find the left and the right-hand side Riemann sum, that's going to give you the two boundaries of where your area is at. Now, just so you can see it, this one is the middle rectangle. So again, this shouldn't say R1, this should say M1. So that's 1, that's 2, 3. Notice that the points that hits the graph is in the middle. 3, 4, and 5, and 6. So this one gets 8.65. I don't even know if this is really exact, but it is in the middle of those two. Because the L and the R, those are your upper and lower estimates. Okay? So the more rectangles, the more accurate we are in finding the area underneath the curve. Now, some of you guys don't understand, or you're having a hard time understanding, why would you ever use the L or the R? Like, why not use the M always? Well, the L and the R just, again, they show you the upper and the lower limits of the area, of the estimate. And look at these different endpoints. This one's right endpoints. Just want to show you guys which one looks more accurate. So these ones, at the right side of the rectangles, the curve is touching the right side, and over here is the left side, left endpoints, and right here is the midpoints. So it's touching the middle. Which one looks more accurate to you? The left, right, or the middle? Yeah, middle does look more accurate to me as well. We're going to expand on those a little bit. So I have my right endpoints here, left, and then the middle. Now we kind of talked about this yesterday, and we built this sigma thing. So I'm going to write out what this actually means so that we can see it longhand. We're going to be using sigma notation to help us when finding the limits as the number of these rectangles approaches infinity. So R sub n would equal, actually I'll use a capital N just like the picture, would equal delta x, that's a change in x. Remember the change in x is the distance between, it's the width of the rectangle. And then we're going to multiply this by the things that we're adding together. And so the first time we would do this, it's a lot of iterations. We plug in the j equals 1. So when we plug in j equals 1, we get f of a plus 1 times delta x. And then we would add f of a plus 2 delta x. And so on and so forth. So we keep going up. That's 1, that's 2. The next one's going to be 3, f of a plus 3 delta x. And you keep going. When do we stop? Because there's a stopping point. We stop when we get to the end. So like if it was 1 here, this would be like 5. And so you do this 5 times until you finally get up to 5. I guess you can say n times. And this will give you the right side sums, the right endpoints sum. Okay, you can do the same thing with the left and the middle. Now, what's different about the R and the L? Okay, they both have a delta x. That's an n, and this is an n minus 1. This one starts at 1, this one starts at 0. Why do they start at different points? I mean, if I was doing the L, it would look like this. I would say L of capital N, you have delta x. The first f that I have would be f of a. And I wouldn't have a delta x because I would be multiplying it by 0. There would be no, like I wouldn't be adding a change. The next one would be f of a plus 1 delta x. So then I'd add one more. And then so on and so forth. We continue the pattern as we see above. Yes? You're correct. Right here, for the right side, we're starting with a plus delta x. A is the start of the interval. So we start with a plus delta x. This one we start with a. And then we do a plus delta x. And then when we get all the way to the end, we don't do the last end point, which is the end of our interval, because this would be our last point. So that's why we start at 0 instead of 1, and we end at n minus 1 instead of n. Okay, so you guys see the difference between these two sigmas right here? Now this one right here is the weirdest one of all of them, because you have to take half of the delta x to add to the a to find this point. So like for example, I would plug 1 into j. That'd be 1 minus 1 half, and so you'd have 1 half times delta x. So you would just be adding half of delta x right here to get this first point. Then if I plug in 2, you're going to be multiplying delta x by 1.5, which would take you all the way over to this point. And those are the points you're plugging into the middle, or they wouldn't be endpoints, the midpoint of the rectangles. All right, so let's do an example. I'll say this for the other video.